times SUT for others kind of alloys. And then we were talking about corrected endurance limit. So it has to be corrected for K size or K surface, K size, K load, K reliability, K temperature times SE divided by stress concentration factor, or the not sensitivity factor related actual stress intensity factor. So based on this, we have given different tables and we have corrected it. Based on this concept, we have two design methodologies. The first one is for a infinite life. For infinite life, we use corrected endurance limit, whereas for a finite life, what we have done is little more different. Of number of cycles and what we did was we drawn a straight line till the endurance point and another straight line from this. So this point was corresponding to number 6, whereas this one was corresponding to 3, and this point is log 10.9 SUT, and this one is SE, log 10 SE. So if we have, let's say, a value of n which is 4.5, which comes at, let's say this is 4, this is 5. So if you want to estimate somewhere here, what we'll do is we'll draw a line here and then we'll estimate, we'll interpolate this value which is log 10 SF. So this is what we obtain for a given number of cycles. So this is for a case when there is complete reversal of fluctuating loads. That means we have designed for such a kind of system in which our sigma max and sigma min are same but opposite sign. This is sigma max, this is sigma min, they both are same, such that sigma mean is equals to sigma max plus sigma min divided by 2 is equals to 0. So your this is also your sigma mean, this is also 0. So this is the value. Now let us see that this is only for one single loading. Sometimes what happens is in a shaft or any machine component can get operated at different lives. For example, if you look at an automobile shaft, at different gears you have different RPM, right? So that's the reason it is not always run at 1 RPM. That means at different, if you're running a whole thing at only first gear, it will have some life. If you're only running something at the 5th gear, you'll have something. But you know that in general 30% of the time maybe it is spent on the first gear, 20% is on the second gear, and so on and so forth. Will be giving you the actual practice. So next thing what we'll do is we will still work with the completely reverse load, but the next thing what we'll do is when we have more than one kind of loading that is available. Okay, so let's start working on this complete reversal of the load, but when you have a more than one levels of load that is operating. So consider in which a component is subjected to different stress levels under fatigue. We want to know, question is how to design such component. So in order to do that, minor, so we will call it as Miner's equation for cumulative damage in fatigue. So this is what we'll learn today, and after that we'll also deal with a case when there is non-complete reversal load. Okay, so let us look at first Miner's equation when you have different stress levels. So the cumulative damage, so with there we have to calculate what is the damage done by first level, second level, so on at different levels. So first we have to define the cumulative damage. So cumulative damage is calculated by summing the contribution from each work cycle using Miner's equation. So suppose a component is subjected to completely reversed stress stresses sigma 1 for n1 cycles and sigma 2 for n2 cycles plus so on like that, we have sigma m, let's not use m, sigma x for nx cycles, are the different levels of the loading for such kind of. So at sigma 1 level of complete reversal, so in this case it would be like sigma 1 and minus sigma 1, it's a complete reversal of load. For this one it is sigma 2 and minus sigma 2, complete reversal of the loading. Similarly, so on like that, everything you will have, mean stress is 0, sigma mean is equals to 0 in this case, sigma mean is also 0 in this case. But in this kind of cycles are there as n1 in number, and these cycles are there in n2 in number, so on and so forth. Sigma x is there for nx cycles. So then we need to calculate the cumulative damage. Before we calculate cumulative damage, we need to calculate what is the amount of damage or contribution to the damage per individual cycles. So let n1 be the number of stress cycles for fatigue when only sigma 1 is acting. So n1 will be the life of the cycle, or similarly n2 for sigma 2, level of stress, so on capital Nx for sigma x, level of stress. So if only sigma 2 is operating on the component will fail after a capital N2 number of cycles. Similarly, if sigma x alone is working, then it will fail for capital Nx. So this information we will know because we know the SN curve for a given stress level. So now we will compute for one stress cycle of sigma 1 of its life is consumed. So for small n1, the total number of life consumed is n1 by n1 life is consumed for n1 cycles of sigma 1. So by induction principle, we can say that the total life can be given by n1 by n1 is life is consumed of the fractional form, and n2 by n2 is coming from the second level, n3 by capital N3 for the third, and so on as nx by capital Nx. Since these are fraction, the sum of all the fraction has to be equal to 1. So, or in other words, we can write in fractions of total number of cycles are given by, so this guy is like alpha 1, and or we can say that alpha 1 plus alpha 2 plus so on plus alpha x is equals to 1. And further we know that, let's say, the cumulative number of cycles can be given as n1 plus n2 equals to, let us call it as a capital N. In that case, using this and this formula, using these two, we can rewrite this fellow as alpha 1 n1 plus alpha 2 n2 plus n3 plus alpha x nx is equals to 1 over n. Right? See, that is what we can write it based on this principle. So these set of equations are called as Miner's equation for cumulative damage, because 1 over n gives the life of one equivalent mixed cycle. So this is how this okay, now what we'll do is we will try to understand since we will try to understand this guy through an example. So since this concept looks a little bit weird, I will again go through it before we go to the example. See, we have a stress like sigma 1 level with n1 cycle, sigma 2 n2, sigma x nx and so on kind of things. So we want to find out what is the life of this mixed cycle and how many number of cycles in this mixed loading it would take care. So we know that in principle the life for one cycle of sigma 1 is 1 over n1. So if we have n1 cycles, then the total life consumed is n1 by n1. So that is the things that is consumed by this fellow, and this is n2 by n2, n3 by n3, and so on like that. But we also know that the sum of all this, since we call it as alpha, is equals to 1, and we have this relationship. So we have this relationship where we give n1 is equals to alpha 1 fraction times of n, and n2 is alpha 2 fraction of so on like that. When you take this equation and substitute in this, then this equation is same as this one. When you substitute these kind of things into that, you can automatically get this thing. So this is nothing but for a mixed cycle of loading, what is the life consumed per one such a mixed cycle? Okay, so see, this is what what will help us in designing for the cumulative design under different levels of the load. So with this, what we'll do, we will try to kind of understand this example using a example which help us to understand this in a much better form. So for that, let us take this example. The work cycle of a mechanical component subjected to completely reversed bending stresses consists of the following three elements. First one, plus or minus 350 Newton per mm square for 85% of time, and plus or minus 400 Newton per mm square for 12% of time, and plus or minus 500 Newton per mm square for the remaining 3% of time. Further, the material for the component is 50 C4 so whose SUT would be around 660 Newton per mm square, and corrected limit of the corrected endurance limit so we have to determine the life of the component. So this is what we have to find out today. So let us work it out line by line to get the answer. So this is our problem. So sigma 1 level is 350, sigma operated at percentage of 85% of the time, and 400 Newton per mm square, which is sigma 2 operated at alpha 2, which is 12%, and sigma 3, which is 500, operated at 3% of the time. SUT is equals to 660 Newton per mm square. SE is 280 Newton construct. Let us construct the SN diagram. If you construct SN diagram in the log 10 ST log 10 N, we know that this point is log 10.9 times SUT, and this point is log 10 SE. We have to join this line, and we know beyond this it would be in this manner. So this point A in our case is .7738. So this point is 2.7. This point is 3, 2.7738, because this is 3, this is 6. So this point is 6, which is 2.4472 is the value. So we got point A and point B. Now we know that we are operating the things at first level is 50 Newton per mm square. So log 10 sigma 1 is equals to log 10. Just a minute. So we'll use different colors. So at sigma 1 is equals 350 Newton per mm square. Log 10 sigma 1 is equals to 350 is 2.5441. So let us make it. So since this is 2.44, so somewhere here we'll have, this is 2.5441 because this point is this component is being operated at sigma 1 at 85% of the time, and sigma 2 at 12%, and sigma 3 at 3% of the time. So if we take log of sigma 1, which is 2.5441, that will hit the ascent curve at this place, and if I take a vertical, this will give log 10. This place will give me log 10 of n1, and the second one will give me the log 10 of n2. Similarly, the third one should give us log 10 of So our aim is to find out n1, n2, and n3. So that is what we are doing. So to do that, so let me just continue further. At sigma 3 Newton per mm square, log 10 of sigma 3 is log 10 of 500, which would yield us 2.6990. So and this one is 2.6021. So at these places, if you intercept the diagram and you take a vertical line from that place, that will give you number of cycles. That's what I'm going to do now. So I will try to compute my n1, n2, n3. So let me try to get it done for one case, and based on that you will understand the remaining cases. So let me call this guy as F point and this point as E point. So we already know E, we want to get F. So at the F, so we will get it something like this using the trigonometric things. EF bar is equals to dB bar into AE bar divided by AD bar. So where you need to know this is the point D, where the endurance point is there. This is the E point at which we want to things using the kind of equation of a straight line and or the similar triangles. One can write this form. So on calculation based on that, you can see this is equals to dB bar is nothing but this is 6 minus 3 and AE is 2.7738 minus, we already calculated E, which is in this case is 2.5541, 2.5441 divided by A, 2.7738 minus D is the point where endurance limit will touch the things, which is 2.4472. That will give us, on calculating EF, now we can write down, but we know that what is EF? EF is nothing but log 10 N1. So on simplification, we can show that log 10 N1 is equals to quickly calculate this thing. So on simplification, we can write N1 after simplification is 128,798 cycles. Similarly, now you can put a new E, which is 2.6021 in this place and recompute your N2. For N2, log 10 N2 minus 2.6021 divided by 2.7738, 2.4472 is equals to 37770 cycles. And log 10 N3 is so actually this is 3 plus log 10 N1. It's okay. So anyway, we are finding out N1 is this is only gives us EF. So this gives you EF. So this is plus 3 has to be added. So 2.7738, because the 3 has to be something like this, because EF is nothing but this fellow. So but log 10 N1 is coming from this place, from the 0, but EF is only this of it. So we have to add for the EF. If you add this 3, then you'll get the corresponding N1. Sorry, the last value is 2.6990 divided by 2.7738 minus 24472 plus 3. Four, 865 cycles. Now we have obtained our N1 as 128,798, N2 as 3,770, N3 as 4,865, and we know alpha 1 is 85% of the time, alpha 2 is 12% of the time, alpha 3 is only 3% of the time. So we know 1 over n is equals to alpha 1 by n1 plus alpha 2 by n2 plus alpha 3 by n3. So that is 0.85. divided by 128798 plus 0.12 by 3703 divided by 4865. The is equals to 62,723 cycles. This is equivalent for 85% of 350 Newton per mm square plus 12% of 400 Newton per mm square plus 3% of 500 Newton per mm square. This is the life, and this has only meaning when your equivalent loading is being given. So this the mixed the component which is subjected to various different stages of stress levels which are completely reversed has a life of 6 to 7 to 3 kind of stuff. Okay, so this is what is kind of required when you are kind of designing for a component with various stages. So with this, the example of example as well as the theory for the completely reversed cycle is done. But one has to understand that not always the stress cycles are completely reversed, and not all the time the amplitude is same. The amplitude can be changing. The mean value need not be zero. It can be positive. It can be negative, and all these factors will lead to kind of deviation from the above theory. Okay, so now we also have to understand what happens that is stresses are reversed. So the above theory will break down because your endurance limit will change when you have the mean stress non-zero, and it will then also depend upon the amplitude. So based on that, we will give certain theories to handle the cases of fluctuating stress with non-zero mean. So non-zero mean stress has an effect on fatigue failure when it is present with an alternating component. So if we plot sigma A and sigma M, where sigma M is equals to max plus min by 2 and sigma A is sigma max minus sigma min is the amplitude. So when you have these things, and if you generally try to plot the failures, you see that if this is an endurance limit SE and this value of 0, 0, right, is the 0, then there is no failure. But when there a sigma mean is 0, you know that the failure happens at SC. So that is what we have studied in the previous case for one loading cases. So, but if sigma m is not equals to 0, that is when we move along this line, the failure curves are generally plotted. The failure points have seen something like are kind of staggered across. Something like this. Each one are failure points. So these are the experimental or actual observations. In order to account for this, several people has come up with several theories. So what we'll do is we will try to understand some of those things in today's class. Okay. So the typical thing is when higher values of mean stress are present, the failure occurs at lower alternating component. See, this is the thing. At higher values of the things, lower values of amplitude it was failing. So this is the observation from the experimental point. So in order to understand this, several people has come up with the things. The first thing is Soderbergh line. In the Soderbergh line is a model in which it is a line joining SC on the ordinate to ordinate is SYT on the abscissa or x coordinate. So that means, let me redraw it. and your failure points would be distributed all over. Something like that. These are the actual observed failure points. So this line is Soderbergh line. So this Soderbergh line, it is the line joining SC on the ordinate and SYT on the abscissa. As modified Goodman line. In the modified Goodman line, they still start from SE and they draw a line up to SUT. So this is Goodman line. Further, there are several other theories. That one is like Gerber line. In a Gerber line, it is again starting point is SC and the ending point is SUT on the abscissa, but this line is a parabolic curve. And if we want to draw the yield line would go something like this. This is yield line. So there are several different models that are present when you have both sigma m and sigma a. Your actual points would vary something like this. Some are outliers, some are inside. So these kind of things. So let us understand the other parts of the things through equation. We have seen the things. Let us see their equation form also. But let us define the kind of Goodman line. Is a line joining SC on the ordinate and SUT on the abscissa. This is Goodman line. And Gerber line is a parabolic curve joining SC on the ordinate and SUT on the abscissa. Now, generally, if you want to use this in terms of design, then we also need an equation form. So let us write the equation form for different things. So anything as per these different lines, anything that is included inside that line between x and y axis is safe. Anything outside is kind of subjected to fatigue failure. So that is what is the different models propose. So let us understand those things. Further, you need to understand that out of all these things, if you have seen the Gerber line, the Gerber line fits the failure points more closely compared to a Soderbergh line or yield line or a Goodman line. So Gerber line or parabola fits the failure points of the test data in the best way. Further, this Goodman line is beneath the scatter of the failure points, and hence it is safer. Now, equation forms of these theories are Soderbergh line is an equation of straight line with Sm by Syt plus Sa by Se is equals to 1, and the Goodman line is given by Sm by Sut plus Sa by Se is equals to 1, and Gerber curve is given by Sm by Sut whole square plus equals to 1, where your Sm is equals to factor of safety times sigma m, and sigma Sa is factor of safety times sigma a. So one can easily write this thing again based on this definition as sigma m by Syt plus sigma a by Se is equals to 1 by factor of safety. Similarly, this can be written as sigma m divided by Sut plus sigma a divided by Se is equals to 1 by factor of safety. So, well, you can also write this one where it is factor of safety times sigma m by Sut whole square plus sigma A divided by SE is equals to 1 by factor of safety. So this is how are the equation forms. So when somebody wants to design a component which has non-zero mean, then we have to make sure we will use one of the set of equations to calculate our the sigma SE, for which because in this case SE would be much lower compared to when you have sigma m is equals to 0. Okay, so for this what we'll do, we will kind of get an example, and using this example we will try to solve a little problem. So let us note down this problem. So example, a machine component is subjected to fluctuating stress that varies from 40 to 100 Newton per mm square. And the corrected endurance limit stress for the machine component is 270 Newton per mm square. The ultimate tensile strength of the material of the component is 660 Newton per mm square. We need to determine the factor of safety against the static failure. SE is equals to 270 Newton per mm square. So if we use Goodman curve, we know that sigma so all we need to do is put 30 divided by 660. So if you solve for this, you can get factor of safety about 4.6 is the factor of safety that is involved in this problem. So like this, we have studied for the one example. Further, there are certain modifications. For the Goodman curve or Goodman line. So what happens is when at higher values of the mean stress, generally the failure is subjected to yielding rather than the kind of fatigue failure. So in order to correct this one, there are a couple of modifications has been proposed for the modified Goodman curve. So the first one, modified Goodman curve is proposed so that at higher mean stress, the yielding failures are taken into considerations. Okay, there are two different modifications. First type for axial and bending stresses. That would look something like this. See, if you look at it, this SABF is the original ABF line is the Goodman line. But we know DC is yield line. So if you these two lines AB or let's say DBC, ABF and DBC intersect at B. So at higher mean stress, since yielding is the criteria, so you have to reduce it. So AB comes from the Goodman thing, whereas BC is the governed by the yielding. So modified Goodman curve is A, B, C. So this is your modified line, where it will start from here to here, and then this is another bilinear kind of things. So anything inside is not a failure, outside is a failure part. So this is how one has to determine for the first type of failure, which is axial and bending kind of things, which should be of this form. Whereas for torsional thing, the things are a little bit different. So in the fluctuating torsional shear stress, the mean stress does not affect up till certain point, because the failure point looks something different. So we will show that, and based on that, so in torsional loading, the mean stress does not affect the endurance to a larger point, which has been observed experimentally. That's the reason this has been delayed. Instead of following this one, which will be too much conservative, they have taken a horizontal line up to one point, B till where the mean stress doesn't really affect, and from there they follow the yield line. So this is the modified yield locus, and for the fluctuating torsional shear stresses. So this is the kind of modified curves correspondingly for the different things. So these are the further modification for the torsional stresses, whereas this is for the axial and bending. For the axial and bending, the mean stress does affect the endurance, so this keeps on reducing. However, for the torsional, it doesn't. These changes are proposed as per the actual experimental observations, and that's the reason this modification will lead into, even though they are safer, but they are less conservative compared to the modified Goodman or the Soderbergh line. Because if you try to over design it, your sections will become much thicker sections. In order to be economical and still safe, people have come up with further modifications of these things. These can be used further in designing the stresses, in designing the shafts or the beams or bars subjected to different types of loading when you have non-zero mean stress. So, and sometimes you should also have to, because in these cases it is only when you have separate axial loading or separate bending loading or separate what do you call as torsional loading, but in certain scenarios all these three loadings will be acting simultaneously. In those cases we have to deal with something called as combined stresses. In the combined stresses, we have to define what would be our mean stress and the amplitude. So let us define those things, because in general components are subjected to axial bending and torsional loading simultaneously. So in order to deal with it, we have to work with how to calculate fatigue stresses under combined stresses. So given a combined loading situation based on distortional energy theory, or also known as von Mises equivalent theory, we can find our equivalent stress as sigma x minus sigma y whole square plus sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 tau xy square plus tau yz square plus tau zx square under root is the equivalent stress. Similarly, for planar situations, this gets simplified to sigma x square minus sigma x sigma y plus sigma y square plus 3 tau xy square. This is the equivalent loading as per the von Mises. It can be a combined situation there where shear stress can be obtained from the bending, torsional and other things, and actual loading is coming from the longitudinal stuff. So in these cases, we calculate our sigma amplitude equivalent is equals to sigma x amplitude whole square minus sigma x amplitude sigma y amplitude plus sigma square y amplitude plus 3 tau xy amplitude whole square is the amplitude equivalent, and the mean equivalent is given by again the von Mises things, which is sigma x mean square minus sigma x mean sigma y mean plus sigma y mean whole square plus 3 tau xy mean whole square. So unlike for this, we will have one small example before we leave. So let's say an example. In the previous case, in an example, we have asked about X loading with maximum of 40 to 100 Newton per mm square fluctuating stress in Y loading or Y direction. Let us say it is 10 to 80 Newton per mm square fluctuating stress. Then find factor of safety such that sigma SUT is equals to 660 Newton per mm square, and SE is 270 Newton per mm square. Earlier we have only used one part of it. Now we have used, last time we have calculated XA, which is 100 minus 40 by 2, which is 30 Newton per mm square. Sigma X mean is 1 by 2, 100 plus 40, which is 70 Newton per mm square. Now similarly we have to also calculate sigma YA, which is 1/2 of, here it is 80 to 10 or 10 to 80, so 80 minus 10 divided by 2 is 35 Newton per mm square, and sigma ym is equals to 1/2 80 plus 10, which is 45 Newton per mm square. So based on this, we can calculate sigma A is nothing but, using von Mises criteria, it is sigma XA whole square minus sigma XA sigma YA plus sigma YA square. Since we don't have a torsional stress, I have not adding it. Similarly, sigma m is equals to sigma xm whole square sigma xm sigma ym plus sigma ym whole square, that is equals to 30 square minus 30 into 70 plus 70 square, and this is 35 square plus minus 35 45 plus 45 whole square is the value for it. So did I mess up? XM is 70, so let us rewrite it again. So let us rewrite this. XA is 30 whole square minus 30 35 plus 35 whole square root. This one is XM is 70 whole square minus 70 45 plus 45 whole square. So this will be around 32.79 Newton per mm square, whereas this is 61.44 Newton per mm square. So and we know that SA by SM is equals to tan theta is equals to sigma A by sigma M, that is equals to 32.79 divided by 61.44, that is equals to 0.534, or theta is equals to 28.09. So similarly, then we have SA by Sm is equals to tan theta, that is equals to 0.534. That implies your SA is equals to 152. Further, we need to know that this is one thing, and SA by SUT plus SM by SE is equals to 1. That implies SA by this SA by SE plus SM by SUT is equals to implies SA by 270 plus SM by 660 is equals to 1. By solving both the equations together, we can find SA is equals to 152.88 Newton per mm square and SM is equals to 286.29 Newton per mm square, and factor of safety is SA by sigma A, that is 152.88 divided by 32.79, that is equals to 4.66 is the answer. So with this, we have looked into stresses under combined loading as well. So with this, it will finish our chapter on the fluctuating stresses. In the next class, we will start on welding as well as riveted joints. So